Yeah, it is my pleasure to introduce Professor Anandavardhanan for this wonderful achievement. And Professor Anandavardhanan got his MSc in 1998, PhD in 2003, both from University of Hyderabad. And after that, he did his postdoc at TFR during 2003 to 2005. And later, he joined IIT Bombay in July 2005. He is in fact a recipient of many awards, which includes he's an excellent teacher also, Department Excellence in Teaching Award 2016, Excellence in Teaching Award 2010, and he NASI's Scopus Young Scientist Award 2015. He is a founding member Indian National Young Science Academy 2015, NASI Young Scientist Platinum Jubilee Award 2009, INSA Medal for Young Scientist 2008. He is a Young Associate Indian Academy of Sciences for during 2007 and 2011. So I don't want to actually take too much of his time. I'll let him just speak about his work. So Anand, please.
This is the title of the talk. It's distinguished representations. So what I'm planning to do is, of course, I will not get into any detail. Maybe in one slide, I may have some mathematics notations. Other than that, I'm just trying to use photos, pictures of mathematicians to introduce some words without really saying anything about those, just to give an introduction to the area that I work in. And then okay, so that's the plan. And so let's also this doesn't move. Yeah, okay. So let me start by thanking Professors Milindatri and A.M. Pradeep for the invitation to give this presentation. And as I said, I will not get into any technical detail in this talk. Instead, in the first part of the talk, I will introduce a broad area that I belong to via the pictures of a few mathematicians. So slide should have something. So I have put some pictures and I will introduce some words and without any further detail into those words. So this is what I will do in the first part. And in the second part, I will introduce one mathematical object. This will require a little bit of notation, but not much, very elementary. It was studied 200 years ago. This particular object that I will put in my slides, studied long ago, 200 years ago, and narrate a small story via two screenshots. At the very end, the very last slide, I'll state a couple of results in which I am involved, but I'll just project those slides and will say nothing about those. But from the context, maybe something will be clear. All the pictures are lifted from the internet, mostly from the Wikipedia. So, okay, so let's start. On the right, of course, all of you know Srinivasa Ramanujan, and on the left, you have Harish Chandra. Many of you will know the name, but not perhaps all of you. A very famous Ramanujan, I will say nothing because all of us know very well about him. Harish Chandra is also a very, very famous mathematician known for his path-breaking work in various fields of mathematics. Let me just put two words here. Associated to Ramanujan, he has done so many things, but one object that comes in his work a lot, and he has made phenomenal contributions to, is what is called modular forms. Modular forms. And Harish Chandra worked in an area called representation theory of groups, a certain kind of groups, various other techniques, but just for our purposes, the word to remember is group theory, and representations of that. So groups come in chemistry, physics, various places. So these are certain kind of groups here. So these are just the words. Associated to Harish Chandra, we have group representations. Associated to Ramanujan, we have modular forms. Then comes Robert Langlands, a very famous mathematician. This is how I want to introduce my area. The area is called Langlands program. So that's why this picture is coming. And in the mid 1960s, he made some revolutionary insights, some conjectures, some results, a whole gamut of things, which basically connects the two words that I introduced in the last slide, group representations associated to Harish Chandra and modular forms associated to Ramanujan. And these have direct connections to number theory. So this, I can't get into more details in this kind of a talk, but this is roughly late 1960s, early 1970s. Okay, and this is called the Langlands program. A few lines about it. So Langlands program is now one of the most influential theme in number theory. So number theory, as you know, is studying numbers, and this is the way to study number theory, so to say. This is called the Langlands program, named after Robert Langlands. To the extent that to many mathematicians, these two are interchangeable terms. Number theory is Langlands program is number theory. Recall from the last slide that this involves studying representations of certain groups G. I'm just recalling this once again in order to introduce what is called the relative Langlands program. So which is a relative variant of the Langlands program. Of course, it's called the relative Langlands program. And this is broadly my area. And I mean, a narrow part of this vast area is what I do. So I don't know much about the whole area, but what I do belongs to this is a correct statement. The analysis here is carried out not on a group G, but together with a group G, you also have a subgroup H, and analysis is carried out more generally on these quotient spaces G mod X. So not just G, the data consists of a subgroup H also, where H is a subgroup of G. Distinguished representations, which is my title, these are representations of G that contribute to such an analysis. So these are representations. These are the main objects of study in what is called the relative Langlands program. Its origins. So I said Langlands program is late 1960s. The relative Langlands program. The word is very new. Maybe after 2000, I don't know, 12 or 13 or sometime. But its origins can be traced back to the mid 80s, 1980s, and it has acquired even more vigor and verve in more recent years, thanks mainly to a couple of maybe a few more major works in very recent years. I will only have a few more slides of pictures. Already I had Harish Chandra, Ramanujan, and Robert Langlands. I will have a few more slides of pictures as a way of introduction, and I will get to the part 2 of my talk. So Asterisk is not quite a journal. I mean, it is a journal, but which publishes not small papers, but actually research monographs. So I don't know how visible these photos are. This is Asterisk volume 346, published in 2012. So as I said, recent years. And this is Asterisk volume 396, published in 2017. So both relatively recent. There's also 347. I didn't have space to put 3 photos. So 346, 347, and 396. This one is something in French, the title, but it means On the Conjectures of Gros and Prasad 1. 347 would be the same title 2. And this is by Vitek Gan, Benedict Gros, Dipendra Prasad, and Walsperger, French mathematician. And this one is by Yanis Sakellarides and Akshay Venkatesh. I have some numbers, let's leave it there. And these are the photos. So this is Vitek Gan, Benedict Gros, Dipendra Prasad, Walsperger, and Colette Mogla. And Mogla's contribution comes in this volume, 347. This was one of the major works which put relative Langlands program in the in limelight, and the other is the other volume that I mentioned, Yanis Sakellarides and Akshay Venkatesh. By the way, I think this is no, this is not my photo. This photo is also from Wikipedia, not Wikipedia, somewhere on the internet. Yeah. So this was a broad introduction, at least the word relative Langlands program. That's my broad area. Again, I should emphasize that's not that that's my area. I mean, I belong to that area. I mean, it's a vast area, and there are many things which I have absolutely no idea about. But what I do belongs to this. I will very quickly narrate the story from 200 years ago. And the main character here is the legendary old mathematician from 200 years ago, Carl Friedrich Gauss. And you know, you just here is just one slide with some notations. You take numbers up modulo a prime number p, and you also take the non-zero numbers there. So you have 0 to p minus 1, and the second set does not have 0. And The first one behaves well with addition, modulo p, of course, and the second one behaves well with multiplication, modulo p. These are two very different structures. One is addition, one is multiplication, and we would like to mix them up. And how do you mix them up? As follows. So maybe I will not spend much time. You can take what are called homomorphisms. One is additive, one is multiplicative, and put them together and mix it up. Actually, take it in a test tube and mix it up. And it's not difficult to show when chi is of a particular type that this particular quantity, so this is what is called the Gauss sum associated to Gauss. And Gauss observed this in 1801. This is easy. This doesn't need Gauss. That it will be, either plus or minus 1 in this regime and the plus or minus the square root of minus 1 in this regime. Question is, can you figure out the sign? Why plus or minus? Can you fix it? Either it's plus or minus, or when it is what? Here comes the promise story from the first slide. Gauss remarked that in 1801, he knew that he could fix a sign. Both should be positive, but he couldn't do it. He could do it only in 1805, after 4 years. And he published it only in 1811. Proof turned out to be elementary, so that plus or minus, it is the plus. And this is a theorem from 1811. So this is, and just to narrate the story, here is one more episode about it. He wrote to his friend that determination of the sign is a much more difficult problem. The conjecture that the plus sign holds in each case was made by Gauss in 1801, but only in 1805 he could actually prove it. But he remarked that he could prove the very elegant theorem mentioned in 1801, and one of his friends, he apparently wrote that seldom had a week passed for 4 years that he had not tried in vain to prove this conjecture. And here is something in German which is translated as lightning strikes. Finally, in 1805, as lightning strikes was the puzzle solved. Now there are so many proofs. I mean, it's an elementary result. Okay, so last slide. A lot of my work is in the same spirit. So what I basically do is put yourself in a situation where figuring out a certain quantity is not very difficult. Not very difficult up to a sign. The plus or minus, this turns out to be difficult. And then try to fix a precise sign. That's where the difficulty comes. So up to a sign, not so difficult to understand, but figuring out the sign turns out to be difficult in the spirit of the Gauss sum question that I narrated in the last 2 slides. The problems where we fix the sign of certain Gauss-like sums, these are analogs of Gauss sums. This involve distinguished representations of the title, which are the central objects of the relative Langlands program. And I will just flash 1 or 2 of these things without going into any detail, but note that the word distinguished is there. And finally, the result says it is +1. This is not my result. This I conjectured in 2008. It could be plus or minus 1 is easy, but it is +1 was a conjecture which was proved in 2017 by 2 mathematicians, Nader Matranj and Omar Offen, in 2017, that it is indeed true. It is +1. And here is another Gauss-like sum. This one is not the previous one, and this is going to be published next year, 2021. And so it's a many authored paper. I'm one of them. And here also that it is plus or minus 1 is very easy. I mean, not difficult, certainly. And that it is +1, it requires a lot of effort. Okay, I think that's my last slide, and I stop